Good evening, everyone. You are welcome to CHM204 class. Today is the first class of this facilitation. My name is Professor Lain Kajani. I am the facilitator for this course. So I want to welcome every one of us, and I want to wish you very refreshing stay together. In this class, we shall be looking forward to a very good interactive section where everybody should have watched the video for each class before the class, so that based on that video we can have quality interaction and therefore enjoy more learning. I want to believe we have all watched the first video I sent to us with the instruction that you have to watch it before today's class. So on this note, I want to welcome you to the class, and I pray you stay tuned and also stay blessed. This course is that every student should ensure that they interact well with their course material, and then ensure that every time they are coming to class, they must be attentive and be ready to contribute, because the class is expected to be an interactive session. We are not expected to be teaching as in the normal teaching class. That's why before every class, there must be a pre-class activity, which comprises of sending the video for the class you have to attend ahead of that class. It is very important that every student please watch this video and then note everything that are area of concern, so that when we come together, we can solve some problems and then be able to throw it open for everyone to interact and thereby enjoying learning. So the course is CHM204, as I earlier said. The course title is Structure and Bonding. It's a 2-unit course. In the module 1 of this course, it's made up of chemical bonding. The intended learning outcomes today know how to achieve stability through chemical bonding. They should be able to evaluate the attainment of object or duplet configuration as a condition for stability. We should be able to recognize the 2 major types of bonding in compounds. We should be able to also demonstrate the condition needed for the various bonding. They must be able to enumerate the properties of various bonds, and they must be able to know how to evaluate and calculate the lattice energy and the 2 methods of calculation involved. Of course, this one is, as we have said, chemical bonding. We know every chemical system seeks to stabilize with the minimum attainable energy or energy level. And because of this important phenomenon, chemical reaction involve only 2 valence electrons, only the valence electron, and their combination can lead to stability through 2 major processes. The first one is by one atom or element of an atom donating electron to another one. So in this situation, where there's a complete transfer of electron to another, that's what results into ionic bonding. The second process is a place in which the 2 entities involved agree to share their electron in order to make both of them attain the Octet rule. And in a situation where electrons are shared at the boundary, a kind of bonding that exists in such is called covalent bonding. And it's very important that when we are talking about the ionic bonding, what are the major characteristics of ionic bonding? What are the compounds that can exhibit ionic bonding? And what are the various situations that can help us to have more and better information about these systems of phenomena? Ionic bonding. We're supposed to make this an interactive class. But since the students have not come on board, I will start the process while I wait for others to join me later. Ionic, what is ionic bonding? Ionic bonding involves the transfer of the valence electron between atoms. Note the word valence electron. It's not just any electron that can be transferred in ionic bonding. The electrons that are in the valence shell of the orbital of an element, they are the ones that are loosely held onto the system, and they are the ones that require a lower amount of energy to be removed, because the inner shell before them has already attained an octet rule, which is the rule of the greater stability. So they are willing to transfer the outermost electron in order to maintain a better stability of the inner core objects. And any atom that is willing to transfer electron to others, after the electron is transferred, they become positively charged, and those are the metals. And every element that is willing to accept the electron to make its own octet stability, they are the one that when they have received such electron, they become negatively charged, and they are called non-metal. So the positive ion itself that is formed by the metal is called the anion, the cation, while the negative ion formed by the non-metal is called the anion. What does ionic bond require? Ionic bonds actually require an electron donor, which is a metal, and an electron acceptor, which is a non-metal. Metal is the one that loses the electron to become cation, while the non-metal gains electron to be an anion. And when the two of them come together, there's a strong synergy that makes the bond between them to be ionic, which makes it to be very strong. This is the reason why to break such bond, it's not easy. That's why ionic compounds have high melting points, because they were formed through established and the strong bond called ionic bond. An example is sodium reacting with chlorine. Sodium have atomic number of 11. And by so doing, we know that it will have 2 electrons in the innermost shell, followed by 8 electrons in the middle shell, and followed by 1 electron in the outermost shell. And therefore, that 1 electron is disturbing sodium to attain the octet. So he's willing to throw that one away so that the 8 electron in the middle shell can allow him to be more stable. So when sodium is willing to lose 1 electron, having transferred that electron, it becomes sodium ion. So sodium ion is different from sodium atom, because sodium atom has atomic number of 11, the total number of protons is 11, and the total number of electrons is 11. But sodium ion, which is Na+, means that it has lost 1 electron for him to have become Na+1. So sodium ion has even still atomic number of 11, total number of protons 11. However, the number of electrons are no longer 11 because he has lost the last one to become Na+. And then if you look at the chlorine with atomic number of 17, the innermost electron will be 2. The second shell will have 8 electrons, making 10. The third one have 7 electrons, making 17. In that situation, it's easier for chlorine to borrow one electron to that 7 to form 8. So it attains its object rule, which is of better stability. This is easier for him to become chlorine -1 than for him to lose the whole 7 electron in the outermost shell. And therefore, if the chlorine loses one electron, if chlorine gains one electron, then it becomes Cl-1, which is the chloride or chlorine ion. And this chlorine ion now still have the atomic number of 17, the total number of proton of 17, but now electron has been 1 above the normal because of that negative charge. So it's having a total electron of 18. And when these two come together, we form sodium chloride. So sodium chloride is formed as a result of transfer of electron from the metallic element, which is the sodium, to the non-metallic element, which is chlorine. You can see here the explanation of what we just said, that the ionic involves the transfer of valence electron using ionic bond. You can see the sodium up here. You can see the sodium here. When you have sodium ion, when we have sodium atom, it's having 11 proton, 11 electron. So it is completely balanced because proton is positively charged and reside inside the nucleus of the atom. Electron is negatively charged that revolve around the atom in a circular path called orbit. So sodium atom has equal number of proton and electron, means that it's completely balanced. Plus 11 in proton, minus 11 in electron. So such elements are called neutral elements, and they have the overall charge of 0. So that's why we call it an atom. But immediately, the one most loosely held electron at the outermost shell of sodium is lost or donated away from it. You see that it will maintain 8 inner core electron, which makes it to be stable. So at that level now, you see have number of proton to be 11, but electron has lost 1 to become 10. In that situation, you have an ion because the overall charge of this is +1. Why is it +1? The proton is positively charged, which is +11. Electron is negatively charged, which is -10. If you take +11 and take away 10, which is 11 minus 10, you have overall of +1. This is the reason why sodium ion has a valency of +1 and is called the cation. What happened in case of fluorine? Because we are talking about transfer of one electron from sodium. As you can see, they have head arrow, meaning there's only one electron is transferred onto the chlorine. So what happens to chlorine? The chlorine as an atom, if you look at it, it has atomic number of 17, proton number 17, 11, electron number 17. Plus 17 minus 17 will give 0. So chlorine is a neutral element and it has overall charge of 0. However, if you look at the outermost shell of this chlorine, it has 1, 2, 3, 4, 5, 6, 7 electrons. And it needs 8 to maintain the stability of its object. So it's easier for him to borrow 1. So if the 1 electron in sodium is donated to the outermost shell of chlorine, chlorine that have 7 before now has 1, 2, 3, 4, 5, 6, 7, 8. And this now makes chlorine anion, because of additional 1 more electron, has 17 proton, but now 18 electron. And you know, proton is positively charged, electron is negatively charged. So if we say 17 minus 18, it gives us overall charge of -1. That's why chlorine, anion, has overall charge of -1. So the sodium chloride form will just be 1 sodium transferring 1 electron to 1 chlorine. So sodium chloride anytime it's formed is always this. Having known the establishments of sodium of ionic bonds, you should note that it's not all the time that the metal and the non-metal will be in the same ratio. Like, for example, if we are talking about magnesium reacting with chlorine, what will be the ionic compound that will be formed between these two? Magnesium has an atomic number of 12, which can be distributed into 2, 8, 2. So if it's to lose electron to become 8 electrons stable, we need to lose 2. So the cation form of magnesium will be +2. And of course, when you look at chlorine before it's 17, which is 2, 8, 7. Each chlorine need 1 more electron to make 7 to become 8. But magnesium by necessity wants to donate 2 electrons. How can these two come together except they agree? So the agreement that will be between them is that since magnesium wants to donate 2 and chlorine wants to take 1, it will take 2 chlorine to make magnesium happy. So that out of these 2 electrons that is going away from magnesium, 1 can go to the first chlorine to make his 288, and the other one will go to the second to make his own 28. That's why we are saying anytime we are talking about magnesium chloride, it's going to be a magnesium will require 2 chlorine to form the ionic compound. So in case of sodium, you see ratio 1:1 of sodium and chlorine. In case of magnesium, you see ratio 1:2. What causes that is total number of electrons that is to be donated must be completely received by the acceptor. So if the acceptor is not enough, it must bring more of itself to get access to that. Like if we are talking about aluminum chloride, for example, what will be the formula for aluminum chloride? Aluminum has atomic number of 13, which is 283, so it's willing to lose 3. Chlorine has atomic number of 17, which is 287, so it wants to borrow 1. Now, aluminum wants to give 3, chlorine wants to borrow 1. So for them to come together, 3 chlorine will need to bring themselves in order to make aluminum happy. So once that happens, we know the aluminum chloride formula will not be AlCl2, will not be AlCl, but will be AlCl3. These are the principles of ionic bonds, so that if you understand it, you should be able to provide the chemical formula of any ionic compound that form as a result of transfer of electron from one thing to another. Having established that, what are the unique properties of ionic compound? It's very important that if ionic compound has existed as compound, then we must know what are their various features that can make us to physically trace that what this compound stands for is an ionic compound. The first one is that they form crystals. Number 2, they have higher entropy of fusion and vaporization than the molecular compound. Number 3 property is that ionic compounds are hard and brittle because of strong bonding force. Number 4, ionic compounds have high melting points and also high boiling points. If they are solid, they melt at a place or temperature called the melting point. If they are liquid, of course, they boil at temperature called boiling point. But one unique thing about ionic compound, they have high melting and boiling point because of the strength of the bond that held the ions together. Number 5, they dissolve in water and other solvents that are polar or with higher dielectric constant to form electrolytes, which can conduct electricity. So when you do take ionic compound in water, because of their ions property and polar nature of water, they can easily dissolve in water. And when they dissolve in water, they free themselves in ionic form. For example, when you add sodium chloride to water, it will leave the fusion state of being sodium chloride, and it will free itself into ions like sodium ions and chlorine ion. And these sodium and chlorine ions that are in this solution, they are now mobile. Unlike the sodium chloride that is a fused white salt. Now they are now mobile, and the mobile electron residing in them will cause them to conduct electricity. So they are good electrolyte in aqueous medium. Structure of ionic compound. The ions have a regular repeated arrangement, and that repeated arrangement is in particular regular pattern, like an architectural design. We call it ionic lattice. Ionic crystal consists of ions which are bound together by strong electrostatic attraction. The arrangement of this ion is in a regular pattern of geometrical structural shape, which I've said is called the crystal lattice. Like for example, if you look at sodium chloride here by the side, you can see the pattern of arrangement of sodium interwoven with chlorine, chlorine to sodium, sodium to chlorine, chlorine to sodium in that regular and meaningful pattern. There are two common crystal forms for most ionic compounds. These are the sodium chloride and cesium chloride structure. The sodium chloride forms the simple cubic lattice with each type of ions occupying the alternative corner, as you have seen in the structure. And that takes us to the second type of chemical bond that is so valuable in chemistry, and this is called the covalent bonds. What are covalent bonds? Covalent bonds are the phenomena themselves, while covalent bonding, covalent bond are the entity or participant themselves, while the covalent bonding is a phenomenon that shows that bond. So covalent bonding involves the sharing of electrons between two atoms or more. This bonding actually occurs primarily between non-metals. Remember, ionic bond exists and occur between metal and non-metal because metal is willing to transfer excess electron in the outermost shell, and non-metal is willing to accept in order to stabilize the outermost shell. But in covalent bonding, it's bonding that exists between the molecule of an atom of non-metal, because none of them is willing to throw its electron away because they are already non-metal. None of them is willing to accept without collaboration, and that's why we say covalent bonding involves the sharing of the electron. Each party has contribution to what makes them what they have. Each party will not be complete without its neighbor. I'm saying that, for example, if an atom requires an atom A requires 2 electrons to form 8, an atom B requires 2 electrons to form 8. They cannot wish to transfer their 6, but they can drop their 2 electrons at the border in such a way that A can add the 2 electrons of B to its 6 to become 8, and B can add the 2 electrons from A to its own to become 8. And therefore, we can see the formation of a perfect collaboration in such condition. An example, there are various examples of such. The covalent bond leads to formation of single, double, triple, or quadruple bond. Unlike ionic bond that form only a single bond, which has sigma bond, covalent bond, because of the necessary excess of electron they can use to take part in this sharing, then they can have what? Like, for example, if A is using 2 electrons from himself to pacify B, and B is using 2 electrons to pacify A, at that region of their coexistence and collaborations, there's going to be a double bond. If A is donating 3 to make B complete, and B is also donating 3 to make A complete, at their boundary where they drop each of their 3 electrons, they will be having a total of 6 electrons, which is 3 electron pair, and that will lead to a triple bond. That's why we're saying covalent bond, depending on the number of electrons each of the party wants to share, can exist as a single bond, or as a double bond, as a triple bond, and so on. So there are some examples of non-metal combined together that form as a result of covalent bonding. Example of such is phosphorus trichloride. You can look at phosphorus as a non-metal, chlorine as a non-metal. By the time they come together, the compound they form is a molecule, which is PCl3. And then, of course, if we look at this very well, you can establish how and what are the bonds that are formed. Like, for example, when we look at phosphorus as an element has atomic number of 15, which means that in its inner core shell, there's 2 electrons. In its middle shell, there's 8 electrons, making 10. And in its outermost shell, it has 5 electrons. Now, when you look at this phosphorus now, you can see the 5 electrons arranged in such a way that he is willing to have collaboration with something. And what is that thing he wants to have collaboration with? Is chlorine. You remember that each chlorine we have said has 17 electrons, which can be distributed into 2, second shell 8, and third shell 7. So looking at the chlorine, he has 7 electrons in the outermost shell, but he needs 8. So he can position one of his electrons in a way that he can drop it in the border between himself and phosphorus. You can see phosphorus carefully positioning one of his electrons in such a way it can form a border with chlorine. So when we look at this region is the region of collaboration of this chlorine and this phosphorus. So when you have to count this phosphorus now, because he has accommodated 1 electron from chlorine, the total electron in this phosphorus here will now be 1, 2, 3, 4, 5, 6. Yet you still need 2 more. So you reposition this one that makes him to have 1 chlorine more, and reposition this one that makes him to have 1 chlorine more. So when this happens, you discover that the boundary of collaboration between the lower chlorine here and phosphorus is this. And the boundary collaboration between the left-hand side chlorine and phosphorus is here. So when you count this for phosphorus, it's happy because with its 5 electrons and 3 donated by the 3 chlorine, it has 8. So it's shared with it. So phosphorus have 1, 2, 3, 4, 5, 6, 7, 8. So close to phosphorus is happy. From 5 electrons in the outermost shell, by allowing that sharing with extra 3 boundary from 3 chlorine, is now 8. So it's stable, it's obeying the octet rule. Now, the chlorine, when it wants to count its own, 1, 2, 3, 4, 5, 6, 7, plus what the fluorine is sharing with him, making 8. So each of the chlorine is happy, also having 8 electrons in its system. That's why we are saying covalent bond will not involve transfer from one place to another, but sharing at their boundary appropriate number of electrons between the 2 parties to make both parties happy. But each of the parties cannot stand on its own without the party contributing to him. Because what the phosphorus is contributing to chlorine makes chlorine 8 and happy. In the long run, what chlorine is donating to phosphorus, 3 of them, is making phosphorus to be 8 and it's also happy. Covalent bond. There are different ways by which covalent bond can be represented in forms of structure. We can use Lewis representation where the electrons are around, and we use it to establish the nature of bond that we have. However, another notation that we can use Bohr notation. The Bohr notation is using Niels Bohr's model of an atom to represent what each of the elements or compound stands for. Like, for example, if you look at the hydrogen molecule, you know that each one of the hydrogen atom has only 1 electron. It cannot obey duplex rule on its own. But when it shares with the second hydrogen, each one of them will have 2 and they are happy. So, but anytime you are using the valence electronic configuration of the shell to denote how the sharing is done to get your molecule, then you are using Bohr notation. Like, for example, when we look at fluorine has atomic number of 9, which makes it to have 2 inner core electrons and 7 outermost electrons. If the 7 outermost electron of the first fluorine position is 1 electron in such a way to have a boundary with the second fluorine, what happened? What we see happen here is that fluorine here is having 1, 2, 3, 4, 5, 6, and 7. He intentionally positioned that 1 that make it 7, so that if you partner with another one from outside, 8 is complete. The same thing with the second fluorine, 1, 2, 3, 4, 5, 6, 7. By the time this partner at this shell region, when you want to count for this first fluorine now, it will be 1, 2, 3 to 7. Count this one to be 8. If you count for this fluorine side, you see 1 to 7 here, and we make this 8. So you can see the 2 electrons shared here. They cannot go on their separate way and still be able to maintain their objects. So for this guy, he will count these 2 as if it's his own. Therefore, it's 8. For this guy, he will count these 2 to his 6 as his own. Therefore, it's 8. So when you see fluorine gas, it's a diatomic molecule, which is gas at room temperature. So you can do it for as many compounds as you wish, but you must make sure you are able to establish the clarity of what they need per time, so that you are able to use it to establish the kind of bond they will form. Another way to note to represent a covalent bond is to use Kopper-Kekulé formula. Kopper-Kekulé formula involves the formula that shows each of the shared pair of electrons is represented in form of their line bond form. Of course, we know anytime you have 2 electrons, it's made up of 1 line bond. When you have 4 electrons, it's made up of 2 line bond. So when we look at methane, for example, using the Lewis representation, when you use the Lewis representation for methane, you discover that carbon itself have atomic number of 6, which is 2 electron in internal shell, and then 4 electron in the outermost shell. Whereas each of the carbon need 8 electrons for stability. So what happens is that 1 electron can come from hydrogen to make each part of this place to be true. So if carbon need 4, then it means it will need 4 hydrogen atoms donating to him. When this hydrogen donates its own electron, that's the first one. This hydrogen donates its electron, that's the second. This hydrogen donate 1 electron, that's third. And this hydrogen donate 1 electron. That's it. So each of the hydrogen, if you count the electron he has now, is 2. They are happy. If you now count the number of electrons from the center carbon now, is 8. Is happy. But when you are using the electron dots to represent the nature of the bond around your element or atoms of the element, then you are talking about something like a Lewis representation. But if you know that each pair of bond, each pair of electron, which is 2 electrons in system, is made up of a bond. If you intentionally turn those electrons into a line bond, then you are already using the notation of Kupakekul's formula. So when we look at this methane in the Lewis form, is Kupakekul's formula will be this, where this line between carbon and hydrogen up is made up of 2 electrons, where this line between carbon and hydrogen to the right is made up of 2 electrons, where this line bond between carbon and hydrogen to the left is made up of 2 electrons, where this line bond between carbon and hydrogen downward is made up of 2 electrons. So you can do this for any compound of interest if we understand what happens within them. Like for example, if you're looking at this compound here, the carbon and hydrogen share one electron, this becomes a real line bond. When you turn it to a line bond, then you are working with Kupakekul's formula. So this Lewis, this is Kupakekul's formula. You can see here between carbon and carbon that there are 4 electrons. So these first 2 form a single bond. This second 2 form a single bond, which makes you to know that alkene is made up of a double bonded carbon-carbon. And that double bond is made up of 1 sigma bond, and the other one is a pi bond. And we know that sigma bond is stronger than pi, and pi bond is weaker than sigma bond. So this is another way to represent the structure of covalent bond. That's Kupakekul's formula. And that takes us to the lattice energy. We have said before that there's a regular pattern of arrangements that allow for compartment of the ions of the cation and the ions of the anion, and that confined a regular pattern of architecture, and then strength is conferred on such. So what is lattice energy? Lattice energy can be simply defined as a measure of the bond strength in an ionic compound. Of course, ionic compound has been formed first. They're measuring their strength, they are measuring their lattice energy, because it is the energy that must be overcome before the molecule of that solid breaks down. That's why we're saying the lattice energy will be high, meaning that the melting point will also be high. So what's just the implication of lattice energy? It actually estimates the bond strength in an ionic compound. It is also defined as the heat of formation for ions of opposite charge in the gaseous phase, in order for them to combine into an ionic solid. And you should note that this combination is an exothermic reaction. Exothermic reaction, of course, is a reaction that liberates heat. Why? Because its change in entropy is always negative. Of course, you know the opposite of it is endothermic reaction, which absorbs heat. That is not what we are talking here, because endothermic reaction have a positive delta H, because the entropy, change in entropy is positive, because the entropy of the products in endothermics is always higher than the entropy of the reactant. But that's not what is obtainable. Like for example, in the lattice energy, you see sodium ion in the gaseous state fusing on chlorine ion in gaseous state to form sodium chloride solid. You can see the change in entropy of that is minus 787.3 kilojoule per mole. That takes us to the first class activity. We are saying, are these compound ionic or covalent? First one, methane. Second one, iron oxide. Third one, iodine. Fourth one, water. Fifth one, ammonia. And sixth one is magnesium chloride. The first thing that you quickly look at as an hint in such is to look at what are the elements that form this compound. Are both elements or all the elements non-metals? If they are non-metal, you know that non-metal is hungry to get electron. So it will not have access to transfer electron to anything. So it cannot be an ionic. But if there is the second thing, that if it can willingly share at the electron at their boundary to form electron density that will make each of them to now be complete, but without their neighbor, they cannot be complete. Then it's also going to be tending to covalent bond. So let's look at the first one. The methane is made up of 2 elements, 1 carbon and 4 hydrogen. And we know, of course, both of them are strong non-metal tendency. And therefore, we say that's a covalent bond. So when you look at iron oxide, iron of course, is metallic and is combining with oxygen, which is non-metal. So you should know that there can be willingness for the transfer of electron from the iron to the oxygen. So that's going to be an ionic compound. Iodine gas is 2 atoms of iodine as non-metal that comes together, just like hydrogen gas. So it's a covalent bond that it has. Number 2, in the following reaction, indicate whether the reactant and the product are ionic or covalently bonded. Sodium carbonate reacting with calcium carbonate, and the sodium carbonate reacting with calcium chloride, providing us with calcium carbonate and sodium chloride. That is for your attempts. Lattice energy can be effectively calculated because it's involved more than one steps in the reaction. Therefore, there must be a way to constantly sum up the heat in order to know the overall energy. And one of such that is the most acceptable way of getting the total lattice energy calculated is using Born-Haber cycle. Using Born-Haber cycle. Born-Haber process or cycle is actually a method that allows us to observe and analyze energy in a reaction. It mainly helps in describing the formation of ionic compounds from different elements. If it is that, then our Born-Haber cycle has actually found wider application in calculating the entropy and the overall lattice energy of a series of reactions. So lattice energy is the entropy change involved in the formation of an ionic compound from the gaseous ion. Hence, the process we said is exothermic. So Born-Haber cycle applies what is called the Hess law of thermodynamics, or you can say Hess law of constant heat summation to solve the problem involving entropy change. And at the end of that solving, we are able to get the overall energy by considering each of the steps of the reaction all the way. But for example, if we are to analyze the Born-Haber cycle for sodium chloride, if you look at the first stage here, we have done it in form of lettering and also in form of cycle. If you look at the first stage, is that sodium atom, you can see solid sodium, needs to be atomized in order to get to the gaseous state. This will be heat of atomization that is needed with 107 kilojoule per mole. Then when the sodium is now in gaseous state, it's now easier for it to lose its electron. When the sodium is still solid sodium under the paraffin, it will be difficult and not possible to lose its electron. So you have to atomize it to the gaseous form, where then you are able to transform electron from the gas state to the ground state to the excited state. That's why the second stage is the conversion of the gaseous sodium to ionic sodium by losing 1 electron, and the heat there, which is the heat of that required the ionization energy, is 496. However, when we look at this fusing, it will fuse with chlorine, and chlorine does not appear as a monoatomic. Chlorine always appears as a diatomic, which is Cl2, and we need only 1 chlorine for sodium to fuse on. So the first thing concerning sodium is to have the sodium molecule so that we're able to get 1 sodium. in the gaseous form. And the next thing, and that's have energy of 243 kilojoule per mole. And the next thing is that one element of chlorine can now gain electron to electron affinity because of its love for the electron. And the energy required at that time is minus 347. So what will now be the sodium chloride? The heat of formation is 411 kilojoule per mole. So the overall lattice energy of such compound, we have this formula, which if you can substitute each of those steps now, we are able to have the 107 for the solid sodium going to gaseous. And we have the ionization energy. We have it. We have the chlorine, which is actually the negative because it gains the electron. And then after summation, everything, we discover that the answer is 786 kilojoule per mole. And this thing we have expressed in data form here is exactly what has happened in the cycle form. So lattice energy can also be calculated using ionic model. Instead of Born-Haber cycle, you can use ionic model to calculate the lattice energy. This method is based actually on the assumption that the crystal is formed from perfect spherical ion. If that assumption is not in place, then we cannot make use of this model. So the fundamental assumption that makes ionic model to be effective for lattice energy calculation is that we need to assume that every of the crystal is forming a perfect spherical ion. No other shape will be able to do because we are going to calculate the diameter, the radius, and all those things. So if we are not seeing it as random spherical, then we are not able to make use of ionic model. So that's the main limitation of ionic model. You can only use when you are not able to assume perfect spherical shape for the ion. The only interaction is due to electrostatic force between the ions. Therefore, it sums up within a few parameters, unlike the other one that has about 5 different parameters. It's based on the fact that they are intact together because there's electrostatic force between them. So for an ion pair, the energy needed to separate the ions depends on the sum of the ionic radii on the product of the ionic charge. So an increase in ionic charge actually will end up in leading to increase in ionic attraction between them. Because the stronger the charges, the stronger the bond that will be formed. The weaker the charges, the weaker the bond that will be formed. So an increase in ionic charge will lead to an increase in ionic attraction between them. So ionic model for calculation of lattice energy can be expressed in terms of the formula here, as we have seen, where each of those things are well defined. The KMM is a constant, RMN and RXM are the anion and the cation radius respectively, because we have assumed them to be round and spherical in shape. So, and the distance from the center of the nucleus to the circumference is going to be the radius. And because they are in ionic form, so it's going to call the ionic radius. The class activity 2, please attempt this. Mention 2 methods of calculating lattice energy. You remember? We said you can use the what? We can use the Born-Haber cycle and we can use the ionic model. Given the following thermodynamic equation, calculate the standard enthalpy change for the reaction. You have to look at this reaction carefully and know what is the central meeting point. The overall reaction is saying sulfur reacting with oxygen to form SO2. But the stepwise processes that we end up giving us that overall reaction is that sulfur is reacting with 2 mole of oxygen gas to form sulfur trioxide, and that energy is there. And sulfur dioxide is reacting with half mole of oxygen gas to form sulfur trioxide. So you have to look at both sides of your equation and see which one of these things is not originally in the overall equation. This is the overall equation. So we can see that sulfur is in the overall equation. We can see that SO2 is in the overall equation. We can see that oxygen is in the overall equation, but SO3 is not there. But when you look at this overall equation, SO2 is on the right-hand side. But in this equation 2 is on the left-hand side. So in order for us to have this, if you look at this, 1 mole of oxygen here, but if you look at equation 1 and equation 2, in equation 1, you have 1.5 mole of oxygen. In equation 2, you have half mole of oxygen, which means that for you to have 1 mole of oxygen overall, you must have removed half of oxygen gas from 1.5 of oxygen gas. So in so doing, we can say equation 1, sulfur is at the left-hand side where it is in the overall. So we can say equation 1 minus equation 2. What will that be? If you have to minus it, that means the whole of this goes to this side and SO3 comes to this side. And when that happens, you can see that the SO3 will cancel the SO3 and then SO2 will now be in the right place. So let's just look at it together in the solution. See the solution, SO3 giving us this, and S plus this giving us this. By the time you have those equations together, SO3 will cancel SO3. SO3 is on the right hand side. It's on the left hand side here. It's on the right hand there. Yeah, they cancel each other. S is on the right side here. There's nothing on the right side. So S plus nothing will come to the right hand side. S. Let's look at it now. On the right hand side here, we have 3/2 of oxygen. On the left hand side here, we have 1/2 of oxygen. So 3/2. If you take away the 1/2, what you end up having is 1 whole number of oxygen. And that will be on this side because it's 3/2 that is retained. It's 1/2 that have to transfer to that side to take it away from 3/2. That's why it's not -1, but it's +1. And when you come to the other side, this one is retained. It's not going anywhere. So at the end of the day, you discover that the overall equation has been formed by just saying we are taking away this equation 2, this equation 1 from equation 2. And when that happens, you know, remember that your equation 2 is -396, and you want to take away the equation 1, which is -29. And then when that happens, you discover that minus will cancel minus. Minus times minus will come plus. So you have -396 plus 99. And that gives us the overall energy of 297. That is the entropy calculated using Born-Haber cycle. Right, so doing, we have come to the end of the class for today. Before next week, by God's grace, I will have sent you the video that you need to watch before the class so that we can make that next week class as interactive as possible. And please tell other friends of yours that the facilitation for 2-3 have started. And then 1 week is gone already out of the 8 week of facilitation. And you have to also let them know that the attendance is very mandatory for each of these classes because we are going to be taking attendance and be using it judiciously. So today, we will be able to deal with number 1, how atom achieve stability through chemical bonding by sharing the electron to become object or by transferring electron to become object. We have also have understanding of the attainment of orchard and duplex configuration as a condition for the stability. We have seen that in order to establish this stability, there are two major types of bonding that will occur. The ionic bonding, if it's as a result of sharing transfer of electron, and covalent bond if it is as a result of sharing of electron. We have also known the condition that is needed for the various bonding to be established. We have also dealt with the property of various bonds, the ionic and the covalent. And we have also looked at the lattice energy as the energy that is measurable within the crystal of ionic compound formed between the positive and negative ion. And in this, we have used two different methods to do calculation of lattice energy. The first one, we use the Born-Haber cycle, and the second one, we use the ionic model. But we said in the ionic model, there must be a fundamental assumption before it can be usable. And that assumption is that every of the ions of the cation and the anion that's involved in that bonding are seen to be spherical and round in shape. Therefore, we are able to calculate the ionic radius as the distance between the center of the ionic sphere to the circumference. And this note, we have come to the end of the class for today. I want to say thank you for your attention, and God bless you. Have a wonderful night.